Hi everyone and welcome to 3D Revolution. Every day new people are joining the exciting world of 3D printing, and so I thought I would put together this video as a beginner's guide for those just starting out to better understand what things are, how it all works, and then they can move on to my other tutorials to have a closer and better look at specific areas of 3D printing. So let's get started. 3D printing is a form of additive manufacturing where, unlike something like carving or CNC milling, where you're starting with a block of material and removing what you don't need, you're starting with nothing, then building up an object based on a digital file layer by layer. There are many different types of 3D printing, but there are three main ones in use. There's SLA, or stereolithography, which uses a laser or projector to solidify a layer of liquid UV reactive resin, and then it moves the bed down and does the same again and builds that up like that. There is SLS, which is selective layer sintering, where it starts with a bed of powdered material, whether it be plastic or even metal, uses a laser to melt a certain area of that, adds a new layer of powder and does the same again. Or there is FDM, which is fused deposition modeling, and that is the most common type of 3D printer for home use. It's almost certainly what you either have just bought or will be getting for your first 3D printer, and that's what we're going to be focusing on in this video. So how does FDM work? Well, FDM uses a reel of filament. It's usually 1.75 millimeters thick, although some devices use 3 millimeter thick filament. And this is usually made of thermoplastic, whether it be PLA or PETG or TPU or something else. But even home FDM printers can use composite materials which take on the properties of other materials they're mixed with, whether that be copper or carbon fiber or even wood. The filament is then fed into the extruder motor, where it is gripped by a sort of spring-loaded cog, and it is then either pushed or pulled by that motor down into the hot end. Now there are two main types of extruder mechanism. There is a direct drive extruder where the motor sits on the mobile carriage on your 3D printer and is directly connected to the hot end, pulling the filament in and pushing it straight through. And then there is the Bowden extruder setup, where the motor will be fitted to a stationary part of your printer, usually the frame, and it will then be pushed along a Bowden tube, which is a long, thin PTFE tube, and that will then be pushed along the tube into the hot end on the carriage of your printer. The main advantage of a Bowden extruder is to have less weight and bulk on that carriage that moves around on your printer. As a result, there is less resistance for the motors that move it around to push against, and there is also less chance of there being vibrations from it translated into your printed model. However, there are issues caused by the Bowden extruder, especially with certain filaments. TPU, for example, which is a type of flexible filament, is much better at being pulled by a direct drive motor than it is being pushed by a Bowden extruder, which is then going to bunch up at the end of the Bowden tube. As a result, about 70%-ish of FDM printers on the market tend to be direct drive these days, but there's definitely an argument for both styles of extrusion. Anyway, the filament is then fed down into the hot end, which has several components. I'm using an example model here, which is a cutaway to show you each individual component and what is happening inside. And this represents the filament. It gets pushed down into the hot end, and the first section that comes across is this big section here with the fins. This is the heat sink. So the purpose of the heatsink is to dissipate any of the heat being generated at the stages lower down that we'll be getting to in a minute, and prevents the filament from becoming malleable or melting earlier on in the process. So the point of this is to keep the filament cool before it's supposed to get hot. Often on the exterior of the heatsink there will be one or more fans blowing cold air over it to further aid in this cooling process. Next, the filament moves down into this, which is the heat break, this dark green part here. And the purpose of this is basically to connect the heat sink that we just looked at with this next part, which is the heater block. We'll look at that in a second. The idea here is to have a solid connection that is reliably stable, but reducing as much as possible the amount of heat that can be transferred between the heater block and the heat sink. Now it starts to get interesting as we move down into this, the heater block. this big grey part here, it is effectively a highly thermally conductive block of metal with holes cut into it and then a number of components fitted into them. The red guy here is the heat element, and he heats up the heater block constantly until he's told to stop. The green guy here is the thermostat, taking a constant temperature reading of the heater block and feeding that information back to the main board on your printer. When your printer has decided that the thermostat has reached the target temperature, it will turn the heater element off. When the thermostat then drops below the target temperature, it will turn the heater block back on, and it will repeat that until your print is finished. Now the next part is where the real magic happens. Now this yellow part at the end here is the nozzle. The filament has already started heating up earlier on in the heater block, and as it enters into the nozzle, it starts to become malleable. It starts to get pushed through, and at the end of the nozzle there is a hole with a much smaller diameter than that of the filament itself. Think toothpaste being squeezed out of a tube. The standard size for these nozzles, the hole at the end is 0.4 millimeters wide, so obviously a lot smaller than the 1.75 millimeters of the filament. But you can also get smaller and larger ones from 0.2 millimeters up to over a millimeter, and that's going to affect the quality that you're able to print at and also the speed. Smaller will increase quality, bigger will increase speed. As the filament is extruded out at the end of your nozzle, it's pressed down into the print bed and it draws a shape on the bed. Once that shape's finished, it's then going to move up a certain amount, and the amount it moves up is referred to as your layer height. Your layer height depends on the settings you've input in your slicing software, which we'll talk about in a minute, but effectively this is the resolution of your print. A smaller number means that it's going to be a much higher quality because it is going to have more information to define any changes in shape. A higher number means that it's going to be a thicker layer and it is going to print much quicker. So average layer height ranges from 0.05 millimeters up to about 0.3 millimeters, depending on whether your priority is detail or speed. It then prints the next layer's shape on top of that and then moves up again, and it will keep on doing that until the print is complete. Now, in addition to the fan or fans that your printer has blowing on the heatsink to cool down the filament before it gets to the heat block, it will also have one or more fans blowing air at the filament as it leaves the nozzle. And the point of this is to cool down and solidify the filament as quickly as possible so it holds its shape as it's being printed. It's more often than not, you'll have your extruder fan turned off for the first layer of the print, and the point of that is to keep the filament more malleable on that bottom layer to aid in adhesion to the print bed. This can also be helped by having a heated print bed, and then as soon as you hit layer 2, the fan is going to kick in and it is going to run for the rest of the print. There are some materials, such as ABS, where you don't necessarily want the cooling fan running, or at least at full power, but for the most part, 99% of materials, you're going to want this running 100% power, 100% of the time after the first layer is complete. So that's how 3D printing works at its very core, but there's still a lot more to it, so let's push on. Your printer is going to vary depending on which exact one you've got, but at its core, you're going to have a X-axis, a Y-axis, and a Z-axis. The files that you put on your 3D printer to start a 3D print are called G-code files, and they are basically a list of commands for your printer. They'll be telling your printer, move the X-axis 15 millimeters, extrude 5 millimeters, heat the heat block to 210 degrees, and lift the Z-axis 0.1 millimeters. One of the most important things you want to make sure is set up correctly on your printer before you start printing is that the print bed is level. That doesn't mean getting a spirit level and checking it against that. You want to make sure that the print bed is perfectly flat in relation to the nozzle. So wherever that nozzle is on the X and Y axes, it should be the exact same height from the print bed below it. The way that you're going to actually adjust the print bed depends on which printer you've got, but more often than not, there is a screw underneath each corner of your print bed, and adjusting that raises or lowers that corner of the bed. So to start with, move the nozzle over one corner, place a piece of paper on the print bed and lower the nozzle onto that paper. Move the paper backwards and forwards, and as soon as you reach a height where there starts to be a bit of resistance between the nozzle and the paper, that's the height you're going for. At which point, move the nozzle up 10 millimeters, over another corner of the print bed, place the paper underneath it, move it down 10 millimeters and start adjusting the corner of the print bed again until you get that same resistance. Repeat this process in every corner of your print bed and then the center, making sure that each of those points has the same level of resistance with the bit of paper as the others. And then you're going to have to probably go through that whole process a couple of times, because every time you adjust one corner, it's going to adjust the amount of pressure on the opposite side. So go through that a few times until you're happy that it is sufficiently leveled. Now, some modern printers don't need manual bed leveling. Ones made by Prusa, for example, have a built-in sensor that measures a grid around your print bed before each print, and it then adjusts the settings internally to account for anything that isn't perfectly level. You can add this functionality to pretty much any FDM printer by buying something called a BLTouch sensor. I'll pop a link in the description below to where you can get these. They're not that much and they're going to make life a lot easier going forwards, making sure you've always got a perfectly level bed. In addition to making sure that your print bed is leveled, you also want to make sure that your nozzle is zeroed at the best height above your bed. Now, this comes under more of a troubleshooting and calibration section of 3D printing, so I'll be covering that in a different video. But for now, just make sure that if your printer doesn't have automatic bed leveling, check what is the best method for your style of printer and make sure that you do that before you start printing. The whole process of 3D printing from design through to a finished product is as follows. You start out with your CAD software, your 3D design software, and you design your model. You would then export that model as maybe an OBJ, or more likely in 3D printing an STL file. You would import your STL file into your choice of slicing software. In there you would have your parameters of your printer, so the size, etc. And you would add the settings for your material and your model, so things like the temperature for your material and the layer height for your model. You would then export the G-code file and transfer that to an SD card or a USB stick to put directly into your printer. Alternatively, if you set up an Octoprint system, you could transfer the G-code file over Wi-Fi directly from your computer, your phone, or even your watch, and then start and monitor the print remotely. Octoprint is basically a remote 3D printer management system running on something like a Raspberry Pi. I've done a number of tutorials on getting started with Octoprint in the past, so I'll pop a link in the description below if you're interested in that. Also, this isn't a tutorial on 3D design, but if you were interested in learning more about CAD, I really recommend on looking into Fusion 360, which is made by Autodesk, and that is one of the best design packages out there for designing 3D models for 3D printing. It is a paid package, but it is free to use if you're only using it for personal use. As for your choice in slicer, there are a few different options to choose from, but there's two main to consider. There's Cura and there's Prusa Slicer. Both of them are completely free, and both of them should work with pretty much any FDM printer you might have. There's also a paid option, which is Simplify 3D. They've been quite quiet for a few years, but they've just released what they say is a big update, so I'll be checking that out and doing some videos on them shortly. Personally, I tend to use Prusa Slicer these days. I've done a number of tutorials on them in the past, and I've also done a beginner's tutorial, which is perfect for those that are wanting to learn what it's all about and how to use it. So I'll pop a link to that in the description below. It's worth quickly noting, earlier I showed you filament being loaded into a printer, but when you unload it, it normally has a little knobble at the end of that filament, and it's good to get into the habit of clipping the end of that filament off, either when you're unloading the filament or just before you load it each time, to make sure that you don't clog your nozzle during that first new extrusion. We've looked at how 3D printing works and the different stages, but let's look at what 3D prints actually are. They're not just solid bits of plastic, and they're also usually not just hollow. They're more strikingly similar to a bird's bone, and they've got this structure inside referred to as infill. This infill can be printed in different patterns, so you can have it just as a grid, or something called gyroidal, which is one of my favourites, or even a more decorative pattern for when your top and bottom layers are quite thin and you can see it for aesthetic purposes. Infill is a pattern printed on the inside of your model between the perimeter walls that provides it with its structure and strength. In your slicing software, the infill will be allocated a percentage, and that is going to denote how dense the infill will be printed. 10% it's going to be quite sparse, and at 90% it's going to be very dense. Obviously the higher percentage, the stronger and heavier it will be, but the longer it's going to take to print and the more material it's going to use. On average, 10 to 25% is going to provide you with more than enough strength and structure inside your print. If you're looking at printing something that really needs to be put under a lot of strain, then 50 to 80% is more likely what you'll be looking for. But you can also, if you don't need any sort of strength for your model, some slicing software will allow you to use something called vase mode, which will print it with 0% infill. It will be completely hollow, and it's very quick to print because it's literally just printing the exterior perimeter, the skin of your model, but there are some caveats to it, so you'll want to look into how to set it up properly if you wanted to use vase mode. In addition to infill, which is printed inside your model, there is also the option to use support material, which is also a scaffolding style structure printed on the outside of your model to support areas which otherwise would just be printed in mid-air. So if I was to print a model of myself with my arm stuck out like this bottom part of my arm is just going to be printed in mid-air. So with support material, it would build up a scaffolding structure below that part. So when it comes to printing my arm, there is something for it to print onto, and then it's designed to be easily removed after the print is complete. If your printer has multiple extruders, you can actually set it to print your support in a different material. You can get water-soluble material, for example, where once your print is finished, you could pop it in some water and your support is going to literally just dissolve away. Now for your first print, you're going to want to print something like a Benchy or a Cali Dragon. I'll pop a link in the description below to both of them, but they're basically calibration models designed to be fun to look at, but to also test your printer in a number of ways, testing how it deals with certain things, and allows you to better calibrate your settings for your next print to achieve a better result. So that's the basics of 3D printing, what it is and how it works. Now you've got a good understanding of the basics, you're going to want to get 3D printing yourself. So the next step is to head over to my Prusa Slicer beginners tutorial, which will take you through the software, how to use it, and getting you started on your first ever 3D print. After that, move on to some of my other tutorials. I can take you through how to set up an Octoprint Raspberry Pi server so you can manage and monitor your prints remotely, or how to do time lapses of your 3D prints. If you've got any questions or if you'd like me to cover anything else, make sure you pop them in the comments below. Otherwise, don't forget to like and subscribe. Thanks for joining me, guys, and I'll see you guys next time.